So our group was given the assignment to develop a rate of penetration controller for a enhanced bit control of a petroleum drill. So to begin, we realized what we needed to do before we could develop a good controller was to develop an effective model for the rate of penetration. And so to do this, we did some research, and we found a model that was developed a few decades ago by Burgoyne and Young, and where they had ROP being a function of 8 individual functions, and each one of these functions had their own parameters and constants, and these constants were generally particular to the oil field. And then 2 of these functions that we noticed were functions of the weight on the bit and the RPM, which were the 2 manipulating variables. We could actually control these up above. And so what we needed to do was develop dynamic models for the weight on bit and the RPM. Originally, we developed both models as simple first-order models, where it was the weight on bit at the top or bottom was equal to the weight on bit at the top times 1 minus e to some negative time constant s or t. And that worked effectively for the weight on bit, and we were actually able to come up with a tuning parameter for that with that tau. But for the RPM, it wasn't a very accurate model, and more research showed that the RPM could be better modeled as a torsional string. Where the entire drill string would be represented as a series of torsional springs. So we were able to model the RPM dynamically using this torsional spring model. And then we also had 2 disturbance variables that we accounted for. One was the pressure on the drill bit, and the other was what we considered ground disturbances, or changes in the rock formations as you drilled deeper. And so with these dynamic models in place, we were able to effectively go and develop a controller to manipulate these variables.
So in order to develop the 2 controllers for the weight on bit and the RPM, we did 2 independent doublet tests. And initially, the weight of bit model has slower dynamics, and so with the initial tuning parameters, it wanted to reach a maximum. Or the top side weight of bit reached a maximum before the RPM did, and we didn't want it to reach a maximum at all. And then second, we figured that the weight on bit would be a variable you want to keep more constant and not vary too much. So we designed the tuning parameters accordingly so that the RPM had the controller would react faster than the weight on bit, and so the RPM would be used if you had small set point changes or disturbances. Or just fine-tune adjustments. So yeah, we tuned the controller so that the weight on bit was a little bit slower, so it would kind of stay at a constant value, and that the RPM would be the one you could change quickly to adjust for changes. Then we also, feedback worked fairly well with 2 independent feedback controllers, but we wanted to try developing a feed-forward controller to see if that would improve the disturbance rejection. So we did that, but the disturbances going into our process model, the dynamics were basically instantaneous, and so we ended up with a feed-forward transfer function that had a higher order numerator, which wasn't possible. So we reduced it to 2 process gains divided by each other. However, as mentioned, the disturbance dynamics into the process were almost instantaneous, whereas the RPM dynamics, which we were using as our feed-forward controlling our parameter to control in a feed-forward controller, it had slower dynamics than the disturbance did in the process, which ended up being basically the same as a feedback controller and getting the same result. And so we went back to a feedback controller because of that.
So for our stability analysis, we tried testing the gains and increasing them, but we found that even after multiplying the weight on bit and the RPM each by factors of thousands, the system still didn't go unstable. And so we figured this was because of the constraints, the physical limits that we put on the weight of bit and the RPM. And so we saw that they were oscillating pretty rigorously, and we didn't want the top side RPM to be maxing out and going to 0 and then maxing out and then going to 0, and the weight on bit hydraulics to go full weight and then pulling back, and that's just not physically possible, or it's not good for the equipment to be doing that. And so we set this yellow as the top side on the graph, and we didn't want the topside function to be oscillating quite so frequently. And so that's what we used in determining our stability, which gave us values that were a lot more physically reasonable.
So as Chris said, we did 2 doublet tests to determine our parameters, and then we fine-tuned them ourselves. And so in the first table there, you see the parameters that we developed for a PI controller. We noticed that the derivative actually had somewhat of a negative impact, adding that term into our controller, so we decided to withhold it and just do a PI controller. And those were the values that we got for the P and I terms for the weight on bit and the RPM. And as James was talking about, we also developed stability limits. We didn't want it to oscillate so much that it would damage equipment, and we found those limits as are demonstrated in table 2.